Hi, this is your video on speech technologies for Entity 318. In this lecture, we're going to cover speech synthesis and text-to-speech. They're basically the same thing. And we're going to talk a bit about speech recognition. Speech synthesis is essentially the process of making computers speak. So let's talk about what speech synthesis actually is and where it's used. And then let's talk about the different forms of speech synthesis. The two main forms are concatenative synthesis and non-concatenative synthesis. And then within non-concatenative synthesis, we have parametric systems and machine learning-based systems. Speech synthesis is just creating artificial speech, usually from text as an input. And it can be useful anytime that you have many things that need to be spoken, but you don't have the time or the resources to actually record native speakers. So we see speech synthesis used a lot in creating synthetic voices for people with impaired speech. I think a really famous example is the Stephen Hawking speech synthesizer, although that was quite outdated by the time he passed. He liked the voice though, so he stuck with it. There's also screen readers for people who are visually impaired. So these are things on your phone that will read out all the available buttons that you can press. And when you press one, it'll tell you what you've pressed and then read the rest of the screen to you. And this can be really important because, as it turns out, actually, a lot of visually impaired people make use of electronic devices like cell phones in their everyday life. There's also the use of personal electronic assistants. So these are things like Siri or Alexa that need to say a lot of different things, and you can't record every single possible sentence in the world. So instead what they do is they create a synthetic voice that allow your machine or your phone or your Amazon Dot or whatever it is to speak whatever text is sent to it. Another really common place that you'll see these is announcements on transit. And the reason for this is essentially that there's a lot of changes that happen in transit. They can add stations, they can take stations away, they can rename stations. And so what they do is, rather than getting someone to record every possible way that they could change things from the start, or having to call someone back to record 20, 30 years down the line, they can simply create a synthetic voice and then just get it to read those texts. We also have the use of speech synthesis for electronic dictionaries. So we saw a bit of this in the last lecture and in the last class meeting. But if you go to most English dictionaries right now and look up a word, there'll be a little speaker icon, and if you click it, it'll read out the word to you. And the way that it's doing this is that it's making use of an artificial voice. They didn't actually get someone to record every possible word. And obviously, for example, sentences, this is even more of a tricky thing to do. With recording someone, it's much easier and much cheaper simply to build a synthetic voice. So why don't we take a look at a few places where speech synthesis is used. This first one is from Vancouver, and it's their SkyTrain line.
This is a Millennium Line train to BCC Clark. This is an Expo Line train to King George. The next station is Main Street, Science World. Exit here for long-distance rail and bus services from Pacific Central Station. The next station is Commercial Broadway. Change here for the Millennium Line. Connect here for the 99B line. Please stand clear of the doors and do not block the doorways.
We won't listen to the whole thing because that's a 3-minute video, but you get the idea there. The synthetic voice is able to create actually any number of sentences that you give to it when it first started, probably didn't have all of the lines planned out because cities don't usually plan like that. Didn't have the names for all of them. You can also add emergency announcements as they come available. I'm actually not even sure that the SkyTrain in Vancouver has a conductor. I think it may be entirely automated, but let's take a look at another example.
May the force be with you.
May the force be with you. I find your lack of faith disturbing.
So there we actually saw an example of both speech synthesis and speech recognition. So the first instance was someone speaking into their phone and it recognized what they said. You'll notice actually that person had an Indian accent. Speech recognition systems are going to have to be made specific to specific accents. And you can make a speech synthesis system have an accent as well. In the second part of the video, what we saw was the system taking in text, which was, I find your lack of faith disturbing, and it turned that into speech. Now let's look at one last example. This one, before we start, I'll mention is a case of someone with a severe speech disability, and it involves speech recognition as well, but then it creates speech synthesis. And essentially, he's able to talk into his phone. The phone will then replicate his speech in a more clear way, and the Hey Google speaker will understand it. Whereas by itself, the Hey Google speaker will not understand his speech.
Hey Google, how many ownership in 1 liter?
Sorry, I'm not sure how to help with that yet.
How many yards in a meter?
Sorry, I'm not sure how to help with that.
How far is San Jose from Sun Valley?
Southern University and A&M College is 645 miles away from Missouri.
What is definition of rhythm?
Here's the definition of rain. Moisture condensed from the atmosphere that falls visibly in separate drops.
This one?
What is definition of rhythm?
Hey Google, what is definition of rhythm?
Here's the definition of rhythm. A strong, regular, repeated pattern of movement or sound.
So you can see there the individual has a pretty intense speech issue. I'm willing to bet this is not just a speech impediment. They likely suffered a stroke or some other brain injury that has caused them to have difficulty vocalizing their thoughts. And it's actually likely that they thought they were speaking correctly. They could understand themselves and they knew what they were trying to say, but it just wasn't coming out. There was some issue with the actual physical process of creating the sounds themselves in the mouth or in the throat. And so by having something that can interpret it, that has a really sophisticated speech recognition system, it can then also create a speech synthesis system so that other people can understand them. And I think this is, a really cool technology and a really cool way to use the technology that has applications all over the place and for many languages. Because if any of you have ever spoken with someone who has aphasia or disordered speech, particularly people who have had a stroke later in life, it's extremely frustrating for them because they're mostly there at the very least in their head. They know what they're trying to say, but for whatever reason they just can't. So speech synthesis, in addition to being useful for language documentation tasks like dictionary making and instructional videos or instructional sounds on how to pronounce things. It actually has some wide-ranging applications. Let's talk a bit about now the different types of synthesis. So we have concatenative and non-concatenative ways of synthesizing speech. Concatenative synthesis is basically just piecing together existing chunks. So these are pre-recorded bits, and it requires more data than the other options. So basically, you have to have a bunch of different chunks of speech. They can be syllables, they can be individual sounds, they can be sentences, although that's going to be tricky if you have it at that high of a level. And you have a database of those or a store of those, and you basically just choose, okay, I'm going to take the sounds that I need and sort of glue them together or put them together like Lego. Once you've glued them together, you can apply some sort of pitch correction to make things sound more natural. So for example, in English, when we speak, even if you took a bunch of individual words that I've said, if you don't have the right intonation, it's going to be hard to make it sound like a question. So if I just say, "What is your name?" doesn't sound quite as good as "What is your name?" And so you're going to have to do some post-processing. But at its base, concatenation is just adding or gluing things together, putting things together. And so we can see in this diagram, we can just ignore the MFCC stuff, but basically they have recordings of hey or he, city, cake, and carry. And they can then take the H from the he and the A from cake and put those together to create hey. This is similar to a lot of early ways of doing speech synthesis. It can create somewhat robotic voices, but they're usually not too bad nowadays. But again, you're going to have a recording of all of the sounds that you want. And ideally, what you really want actually is to use these 2-letter chunks or these 2 sound chunks. So you're not just going to extract just the sound h or just the sound s from city. You're going to extract what we call diphones. And so you'll extract the sound hey from hey, and se from city, and t from city, and even the in-between thing, it from city. So what you'll actually be getting are these 2 sound clusters, and these will be the things that you base them on. So then if you wanted to say hey, you could just grab hey from your store. But if you wanted to say something like cake, you'd have to get the word, some word that has K at the beginning, and then some word that has K at the end. Now remember, because you're not just having a single recording of K, you can't just get the K sound, you have to get it word finally, we call it. Anyways, the concatenative synthesis method prior to 2013 was used in most automated speech systems, at least in some form or another. They were able to, at least for majority languages, get really, really, really big corpuses or databases of sounds, and then they were able to just pick and choose what they needed, and they could make it sound good. Or, as we saw in some of the previous examples, those voices sounded somewhat robotic, so you might not even need to try to make it all that much nicer. So here's what good concatenative synthesis sounds like today.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser. Aspects of the sublime in English poetry and painting, 1770 to 1850.
So you can see these sound pretty good. They're something that you'd hear on your phone. They're clearly not human speech, though. That's not something that I think they're particularly trying to be. They're trying to get close, but they don't want to fool anyone. And they wouldn't, because they sound very robotic. And that makes sense. It's sort of like when you put together a collage, it doesn't look like you drew all the things yourself. Pretty much the same idea here. Concatenative synthesis can be thought of as collaging your sounds. Concatenative synthesis is attractive to researchers and to developers because historically it's been a bit easier. As long as you have a bunch of sounds, all you have to do is go through and chunk everything out. Now that takes the most amount of time. But beyond that, you can just sort of take these sounds, associate them with letters, and then automatically say, if you see these letters, grab these sounds. It generally produced a better synthesis than parametric synthesis, which we'll talk about in a few seconds. But it does also require documentation on the phonetics and phonology of a language. So if you have a language that has tone, but that the tone can change depending on where a word appears in a sentence, you're going to need to know that, or something's not going to sound right. This is particularly the case in languages like Japanese, which have tone that is not entirely predictable based entirely on a word. You have to have the full sentence to figure out where is this tone going to go. So it requires both a lot of data about the language, documentation, but then also lots of recordings from the language. Parametric synthesis, on the other hand, is not concerned with piecing together sounds. What it tries to do is create rules or parameters, I'm just going to call them rules, that allow you to tell a computer how to create a sound. So a very rudimentary form of this, not dealing with computers, might be that if you have a tube and you blow into it, the longer the tube is, the deeper your sound is going to be. And so you could tell a computer, for example, blow into a tube of this length to create this sound. Now, obviously, speech is a lot more complicated than that. This is why parametric synthesis hasn't really been perfected yet. We don't entirely understand how the human speech system works, so we cannot get a perfect parametric system. We cannot tell a computer exactly how to recreate the sounds we want, because even with the science that we have, we're not entirely sure how we're doing it. Then there's the issue of we're not entirely sure how we hear the sounds. So even if we produce them in the right way, would other people hear them properly? Or is there some unique human quality to them? Parametric synthesis is good because it only requires as much data as you need to describe the phonetics of a language. So it doesn't really matter if you don't have lots of recordings. If you have a really good detailed description, then you don't need lots of recordings. On the other hand, especially nowadays, recordings are not particularly difficult to make, so I'm not really sure of an instance in which you'd have super detailed description but no recordings, but historically that was something that may have happened. Now, the downside to parametric synthesis is that you do need to be a bit of an expert in acoustic phonetics, so the actual speech sound sciences, and it can often require more coding because although with concatenative synthesis people have created programs that may allow you to do things a bit more simply, parametric synthesis is still at its heart computer programming. So let's listen to some examples of parametric synthesis.
The Blue Lagoon is a 1980 American romance and adventure film directed by Randall Kleiser. Aspects of the Sublime in English Poetry and Painting, 1770 to 1850.
Now let's go back to the concatenative synthesis.
Aspects of the Sublime in English Poetry and Painting, 1770 to 1850. Aspects of the Sublime in English Poetry and Painting, 1770 to 1850.
To me, at least, they both still sound very robotic, although differently robotic. They're both very good. These are both very good systems. They're trained on English, which has tons and tons of research into it, so that's not surprising. Parametric synthesis tends to be a bit more difficult because you need to have expertise in both programming and in speech science. It does require less data, at least less recordings to build the models, requires more description, and often produces less pleasant results in languages with lots of data available. And what that means is if you have lots of recordings, then you'll probably get a better voice from a concatenative synthesis. Or if you have not a good description of the phonetics and phonology of a language, you're not going to be able to do a parametric synthesis. So now let's talk about machine learning systems. Machine learning systems are like parametric in that they are non-concatenative. They are not made using pre-recorded, stitched together pieces of sound. So it's not like a collage. Instead, machine learning systems require hours of naturalish data. So ideally you want someone reading a book for hours, reading a series of books for hours. And what you then do is you split all of this speech into a few second utterances. So we say utterances because these can be multi-words, they can be single words if the word is long, but they're single word utterances. Then you need to match those chunks of sound, those utterances, with an accurate transcription. So you're not doing each individual syllable or diphone or sound as you would in concatenative synthesis. What you're doing here is you're labeling the full utterance. So if your utterance was someone saying, "Hello, my name is Steve," you wouldn't need to break that up into its constituent sounds. You could just have a label that says, "Hi, my name is Steve," or "Hello, my name is Steve." And these can create really, really good voices. So to just reiterate the pipeline again, we have generally a large file of sound. We split that up into individual utterances. We pair those utterances with a transcription. And the way that we do this is really simple. We just name them the same thing. So, for example, 4.wave and 4.text, because they have the same name, just the number 4, we know that that text file goes with that wave file. And in 4.text, we would have the writing for Apoikaya, and then etc. I'm going to butcher that, so I won't go on for right now. But in the wave file, we just have the sound version.
Apoikaya kis ginawa pamatomatsatsa.
And it doesn't really matter what writing system you use, as long as you're consistent, and recognize that the writing system that you use to transcribe the utterances is the writing system that you're going to have to use to produce utterances. But so basically, we have this step where we pair utterances to transcriptions, and this can be one of the longer steps. The splitting of utterances is generally something that can be done semi-automatically, but then pairing transcription to the sound file, it can be done automatically if you're lucky, but in most cases it can't, and you have to do that by hand. So you give this associated pairing to a computer, which then associates the sounds from the files with the text from the appropriate file. And it learns. It figures out, we're not entirely sure how it figures out, this is artificial intelligence, it figures out the association between sound and writing, and it produces a synthetic voice that you can create things from. So again, this requires hours of naturalist data. When I did this, I used 2 hours of data. Luckily, I had a single speaker reading the entire Bible, as far as I can tell, or at the very least Psalms. And this was freely available, and we contacted the author, well, the speaker, not so much the author of the Bible, the speaker of the Bible, and we contacted the Canadian Bible Society, which was holding the recordings, and asked, "Are you okay with us doing this?" And we got everyone's okay, so I'm going to show you the voices that were produced from that.
Kikisi kinik minos. Kikisi kinik minos. Atemkiwi saskamohitin. Atemkiwi saskamohitin. Isqueo pikiskatisu. Isqueo pikiskatisu.
So these voices are absolutely synthetic. No one's going to be fooled into thinking they are a real person. I will say, though, I presented this and somebody from the Canadian Bible Society was there, and they said, oh, that's, and then the speaker's name. Because even with this artificiality, they could tell the speaker that it was trained on. So these are decent voices. I've tried this out on a few Cree speakers. It's gone okay. Again, they're not perfect. They're not, super pleasant to listen to, but they are okay. And this was done with a sort of past generation system. So machine learning has come a long way since the materials used for this. So I'm willing to bet if we used exactly the same data, we could produce something better now. But also we could add more data to it. So that was speech synthesis. It's a bit of a whirlwind, but basically, to summarize, you have concatenative synthesis, which is collaging together pre-existing sounds. And then you have non-concatenative synthesis, which is either creating rules that tell a computer how to make sounds, or using machine learning to automatically figure out how to get a computer to make sounds. The system of machine learning is something that is going to require some programming experience, but honestly, the difficult part of it for most people is getting the associations between sound and transcription. So that step is one where I think, community linguists in general really can help. They can do it faster, they can do it better. And native speakers can do it better than anybody. So this is a place where I would say we could lend a hand, provided we're working with someone that we trust and that's on the up and up. So now for speech recognition, I'm not going to go into great detail, mostly because you can really think about it as the opposite of speech synthesis. So speech recognition is just recognizing speech. We saw a little bit of it earlier. It usually refers to speech-to-text systems, so making computers transcribe speech. It can be used in personal assistants. It can be used in dictation software, where it's probably most popular. You can use it to automatically write down a story that you've recorded, and it can save you a lot of time. And if it works well, it's awesome. Although whether or not it works well is always... So speech recognition it's generally harder to recognize speech for many speakers than to generate a single voice. So you can create a single voice, you only need to create one, and most people will be able to figure it out. Speech recognition, though, at the very least, you have to appropriately target it for an entire community, at least an accent range. And there's going to be individual variances between how people pronounce things. And so your speech recognition system has to be smart enough or strong enough to recognize those differences, recognize that those differences aren't changing the meaning of a word, and recognize that this is the same word that somebody else said. Speech recognition is basically always done through machine learning nowadays. It's just the standard way of doing things. And for languages that have good speech recognition systems, these are usually majority languages like English, French, German. These are pretty accurate. If anyone's ever used something called Dragon Speech, I think, you'll know it's a fairly decent system. It is okay. It'll get you there most of the time. And again, we saw places where this could be used for people with speech impairments or physical impairments, so someone who can't type very well. We see it in courts a little bit more nowadays. Stenographers are not as common as they used to be. So Let's talk now about how speech recognition actually works, or at least the pipeline. So basically, to start, you have a full speech sample, something that you want to transcribe. That's split up into its components. So we can see on the left, we have a single unit. We split that into 3 components. And then we associate each of those components with computer readable features. So in order to train a system like this, we would have to feed a bunch of speech chunks the appropriate transcription. And in this case, you're probably going to want to actually transcribe each individual letter. It's not just enough to transcribe an entire word. Now, you can have an entire sort of utterance, and then you can just have a word that is split up by characters, and the computer will figure out which character goes to which speech unit. But those systems are a bit more sophisticated. But anyways, so once the computer has associated sounds with particular letters, they then figure out what the computer readable features are. So it's given a waveform like we see on the screen, but a computer then tries to figure out, well, what information is in this waveform? What does this tell me? Once it's done that, it associates that information with the appropriate letter, and then you have an association of features and letters. That's basically your speech recognition system. It's able to hear a waveform and transform that into orthography. So this middle step is, of course, the most complicated one, and it just repeats. Obviously, it's a bit more involved than this. I'm not going into it because we don't really need to know how it gets the information from the waveforms. We just need to know that it does. And keep in mind that especially for speech recognition, these waveforms have to be from a .wav file, because with a .mp3, there's information missing. So if you want to create one of these systems, even for speech synthesis, you're going to want to be feeding it fully complete sound files that have all of the information intact. So as I said before, speech recognition is very hard. Things like background noises, bumping the mic, these can all make it even more difficult. Add into that speech is really quick, and individual speakers can speak at different rates. They can have different ways of pronouncing certain sounds, and you can see how speech recognition is generally more difficult than speech synthesis. So variation between speakers can be enormous. Some systems will only then recognize a specific speaker. These ones are not commercially available usually because it's not super useful. And the differences between even things just like men and women's speech, just in the way that their voices sound, can be so enormous that you have to train individual models on women and on men. And, if you have some sort of speech impediment or, some speech difference, I don't really like the term impediment, that can mess up speech recognition. I'm going to upload these very quickly here. We'll be having a discussion about, so I look forward to you being part of that discussion. If you have any questions, feel free to send me an email. Otherwise, I will see you in class.